So an SO3 invariant tensor is the Levi-Civita epsilon tensor. Okay. So suppose we have, so this tensor transforms as RA, say A prime, R, B, B prime, R, C, C prime, epsilon, A prime, B prime, C prime, right? This is how a rank 3 tensor should transform, right? But we know that the determinant of a 3 by 3 matrix is defined as epsilon, determinant of R, epsilon ABC is equal to RA, A prime, RB, B prime, RCC prime contracted with epsilon, A prime, B prime, C prime, okay? So this is the definition of the determinant. So this is a definition which generalizes to arbitrary dimensions. So instead of, you know, memorizing some mnemonics about row, column, and blah, blah, this is basically this is how a determinant of a matrix is defined, in case you haven't seen this definition before. So if I use this over here, I should get over here the determinant of R, and then we get epsilon A, B, C. But what is the determinant of R for SO3?
One.
Yeah, so we get epsilon ABC. So we see that this thing is another invariant tensor in addition to delta AB. So for SO1, 3, can you suggest a tensor which is analogous to this? It's just a Levi-Civita in 4 dimensions. Okay, so this is defined such that epsilon 0, 1, 2, 3 is +1, and it's -1 for, you know, odd permutations, +1 for even permutations, and that because it's -1 for odd, you know, and whenever and 0 otherwise, right? And again, under a so let me show you why such, you know, why the Levi-Civita is such a useful thing. So let's take a SO3 vector, you know, a vector representation, okay? And let's take another one, so 2. Now, suppose that I consider the antisymmetric combination of these two guys, right? Let's call it Jij. Can someone tell me what is the number of independent components of Jij? Actually, let me, instead of calling it W, let me call it Ri. And instead of calling this V, let me call it Pj. And take the antisymmetric combination, sorry, let me just rewrite this. Ri antisymmetrized with Pj, and the combination I'm going to call Lij. Can someone tell me how many independent components Lij has?
3.
Right. So do you know what Lij is? If Ri is position, Pj is momentum?
Angular momentum.
Yeah, but angular momentum is a vector. Why do we have, but we have a tensor here. How do I make this into a vector, Saif?
You'd have to contract out one of the indices.
Who should I contract it out with?
Not sure.
If I contract, so this is where Levi Civita comes in. If I take I, epsilon I, j, k, L, j, k, and so I can define this in 3 dimensions to be a new object. Let's call it, say, L tilde of I. Okay, and let's see how L tilde transforms. So under a rotation, L tilde will go to L tilde prime, and but according to this definition, we'll have R, J, J prime, R, K, K prime, L, J prime, K prime, epsilon, I, J, K. We know that this is invariant, so I'm not bothering to write the matrices for this guy. Okay, so now we see that we have great. So we have essentially, we have to, now we look at this combination. Okay, so what is R, J, J prime, R, K, K prime, epsilon I, J, I, J, K, okay? So what it is actually easy to show. It's R, just one second. Okay, sorry. Yeah, I misspoke. So basically what we should do here is that if you look at it, we see here, you know, this thing, right? So we have here R, J, J prime, R, sorry, let me get this right. Yeah, okay. Yeah. So, okay, so the identity that we need is the following. So here we have how many index that's free? One index that's free, right? So the way that we can get one index free from one factor I is we have to have some epsilon I, then we have JK, and there will be a factor of JK here. And once we use this over here, what will happen is that this guy, and this guy will give me LJ prime, K prime, R, J, K, just one second. I'm getting things muddled.
Aren't the J prime and K prime also free?
Yeah. Yes, they are. Yeah, you're right. Yeah, sorry. You're right. So it's RJJ prime, RKK prime, epsilon I JK. So we should get there is how many indices are there? There are so JK is JK. So we should have 3 indices, right?
Yeah.
So we should have epsilon. We should have epsilon J K L times R L K. Okay, it's either LK or KL. Okay, it's one or the other. Because the idea is that we can verify. The idea is that if I, so yeah, sorry, that's not what I meant. So this has JK, JK I. So there's there's JK. So there should be an L and I here. Yeah. So I think now it's grammatically correct. And the idea is that, oh, sorry. So the idea is, if I now apply the inverse matrix over here, so I should get RJ, RKK prime, epsilon IJK is equal to epsilon LJK, RLI, and R, MI. So I write RMI here, but RMI and RLI is going to give me delta LM, right? So then I get here epsilon M JK, and over here I have the usual R cubed epsilon, which is the identity we know, right? So that identity and this identity is equivalent. So when we use this over here, what we will have is we'll end up getting, we can replace these guys by a factor of R and a factor of epsilon and a factor of L in such a way that we get R, I, J, L tilde J. Okay, so that we see that this is actually a vector. Okay, so this is basically, so all the algebra aside, what we have done is that epsilon ABC was used to transform an antisymmetric, a rank 2 tensor into a vector. Okay, this is basically the magic of cross product, right? The cross product is nothing but this thing. So we know that L is a cross product with an R and P, right? That's exactly what we have done. Incidentally, L is a vector under SO3, but not a vector under O3. So what does that mean? So if I take a parity transformation, which is in O3, but not in SO3, then R goes to minus R, right? And P goes to minus P. But because L is R cross P, this actually under a parity does not flip sign. So these are vectors, whereas L is what is known as a pseudo vector. Okay. It's also known as an axial vector. So pseudo vectors are like vectors under SO3, but under parity, under the discrete transformations of the expanded group, they act in a way that is different from the vectors. Okay.